Now let's go through quadratic surfaces. So quadratic surfaces basically is the three-dimensional version or cases of conic sections. When you do conic sections, you really are looking at cones and taking a plane and cutting through a cone, and you get the parabola, hyperbola, ellipse, and spheres. So what this is the three-dimensional versions of those, and really more practical in everyday life, really, or applications and such. So the basic form is basically the ax squared plus b equals a constant, but we add another variable. So this is the form of what a quadratic surface would be: ax squared plus by squared plus cz squared plus d z equal to e. Now this just basically shifts stuff vertically along the z-axis. So if you left this off, and there's actually a larger form of this that shifts it all around, but we really keep things at the origin, or we might just shift it usually up along the z-axis, up or down. So if you complete the square on z, that's what the dz part ends up doing, is just shifting along the z-axis. So, but what we want to get basically the basic form of everything, and we're not going to do much shifting right now, or much later either. So let's run through all the different cases and types. So first one we'll look at is called an ellipsoid. So let's write those down, and then I'll show you what it looks like and what the equation is. So ellipsoid. So ellipsoid is kind of what you would think. It's, looks like an egg, but it's symmetric, so it's not an egg, right? So it's hard not to draw it like an egg either. So that's where you have all the coefficients positive. So ax squared, and we'll use lowercase, over a squared plus y squared over b squared plus z squared over c squared equal to 1. So if you write it in that form, then your ABC gives you the length of basically the axis, along those axes, what's the distance from the origin or distance from the center to those different values, just like an ellipse. So to draw an ellipsoid, depending on what it is, and we're just going to give you all the basic shapes right now. Let's go ahead and change the axis color. So let's do this. So you can draw on this first, or you could draw the ellipsoid and then draw on the axis later. It doesn't really matter how you do it. So, but that is, I don't want to just show it to you. I want to show you how you draw them. So you draw basically, you can do like an ellipse down here. So wait, actually, let me show you how this works. So you can draw like an ellipse, and then this can be moved around the way I have it. And then what you do, if you have something similar, or just looking at what I'm doing, even on paper, is you go in and erase the back. So that's like your dotted portion looking through the ellipse. And then you have what you draw is along like all the way around it. So if you go up to, say, here and down 1, 2, 3, 4, 1, 2, 3, 4, down to here, then you have kind of this shape like this. And that wasn't drawn very well, so you kind of go in and draw like that. And then it's almost like you can even do this, with your pencil. It's sometimes easier to sketch it, because I'm gonna erase a bunch of stuff here and do this same sort of sketch. Try to not make it pointed like that. It kind of is, has that shape to it. And so you go like that. And then now I'm going to go in and erase. I'm going to make this a little bigger, and I'm going to erase. So you can draw like a sketch, or if you're really good with your hands, you can, in sketching stuff, you can make it look a little better. Okay, so it gives you an idea what I want it to see. And then you can draw you draw on this side, and it's dotted in the back. Okay, so that's okay. It's pretty close. Not a very good one today. But there's your ellipse. Let me see if my other one's better enough to show you. So those are the notes I'm using to sketch. That one's a little better. You can see. Okay, but what I drew is good enough. Like, that's totally fine if I ever asked you to draw something. But you do want to be able to sketch these. All right, so next, let's do, I'll leave it there. Let's do what's called, oh, and then almost forgot. If A, B, and C are the same, what do you have? Well, just like a circle, you'd have a sphere. So it would be a sphere, right? And spheres are a little easier to draw. You make everything kind of the same. So you got that, and then you can draw this in. So this is a sphere, much easier to draw than an ellipse, but not to worry. You kind of just get close and label it and you're fine. Okay, so if A equals B equals C, you get a sphere. Just like a circle and an ellipse. Next is what's called a hyperboloid. So you have two cases. So hyperboloid. And we have of what we call one sheet. And then we have a hyperboloid of two sheets. So one and then two sheets. I'm going to just cheat a little bit here and copy it. Okay, so you have one and then two. So hyperboloid of one sheet, this is your basic form. Now I'm only going to show you the case where it's up along the z-axis. But I'll show you different cases where it's along a different axis. So it looks like this. It's x squared over a squared plus y squared over b squared. And then minus, there's your negative, z squared over c squared equal to 1. I'll show you what that looks like. And the hyperboloid of two sheets, there's two negatives in there. Your z is positive, so you put z first. So you say like z squared over c squared. I always like to put, and I don't know if the book does this or not, but I always like to put a under the x, b under the y, and c under the z, regardless of the order. Z squared over c squared minus now x squared over a squared minus those two negatives, y squared over b squared equal to 1. And so hyperboloid of one sheet looks like this. Basically, it's the sides are hyperbolas, but then it looks like well, I'll show you. It looks like this. This time I'm going to draw it where you do like those ellipses. So you can copy that and then paste it. So that's like oh, I just messed that up. Close enough. Okay, so those are like the ends, but it keeps on going, like it doesn't stop. So this is, and then the sides, like this, are hyperbolas. Okay, and then it keeps on going, forever. And in the middle, those are ellipses or circles, depending on the situation. Like the coefficients and stuff. So if A, B, and C are all the same, then those ends up being circles. If they're not, then they're ellipses at that intersection. So you can draw it like that, and then later put in your axes if you want. So I'll do it like that. So I'll go ahead and put in an axis. Let's do it. I don't think this shows up very well. No, it doesn't. Let's do it a different color. Okay, so this comes up like this. There's your Z. There's your X coming out. So you can draw this in after the fact if you want. They go through there, and there. And this part was you draw it like that, where now it comes up right there. Okay. Now, hyperboloid of two sheets basically looks like this. You have the same kind of top and bottom, but then, and I'll try to make this look nice, like that. So these are like little bowls that come down like that. And this one goes up like this. So it's missing stuff in the middle completely. Okay, so that's that your hyperboloid of 1 and 2 sheets, and your axis is in the inside here. So let's do this. There's your z-axis, and this would come out as your x. This would come out as your y. So I didn't draw that very well. Okay, and then there's your y. So there's your 2 sheets. Okay, the next one is the hyperbolic paraboloid. Basically, you have to picture a Pringle. This is hyperbolic paraboloid. And so this one, it's hard to draw this one, but picture a Pringle. It goes like this, and I can't even draw. I never can draw these very well. So we won't. I'll show you a picture. No, I'll show you kind of how you draw them. The graph looks like this. I mean, the equation looks like this, hyperbolic paraboloid. And just for consistent, no, that's fine. All right, so, okay, so this one will write, and it can open in different ways. This one I'll write as y squared over b squared minus x squared over a squared equal to, and then look at z over c. And then c is positive. So basically, what you end up getting, and what I want you to picture is this. What if you had z equal to y squared minus x squared? Okay, so you have that one, and you have z equals x squared minus y squared. So what we're going to do, the way you start graphing these things and picturing them, is what happens if you like cover this up. Then that's just z equals y squared. That's a parabola in the z y plane. And then if you do this, that's a parabola that opens down in the zx plane. And then so they basically shift in different ways. So picture a Pringle, right? How that shape of that is, how it goes. It's a saddle or a Pringle. So it's either a saddle, that's the saddle shape, or Pringle is what we say. So I think for this one, probably best just to show it to you. So this one is this down here. So I'm gonna actually just copy and paste it in there. So this is the hyperbolic paraboloid, just like that. Okay, because it's really tough to draw. You can get in there and try and draw it. You basically do that, and then you do that, and then you try to make the rest kind of connect. And you can see how they do the shading to help that connect. So you do this, and then this, and then you do that, and you can make it happen. But it's I've never been able to do it very well. Usually, if I ever ask you to identify stuff, it's either just tell me what it is, or identify which one's hyperbolic paraboloid. But you can see that's either like a saddle, right, like on a horse, right? So you have the reins or whatever here, and your legs are on both sides, right? Or think of it as a Pringle, where you're going to eat that chip. Okay. Moving on. And I will show you, we'll probably pretty much just look at what's in the book as that's your reference. That's what you want to use. And then how to identify all these. So the next one is a cone. Okay, so what does the cone look like? All right, so let's see. This is the equation, x squared over a squared plus y squared over b squared minus z squared over c squared equal to 0. So let's just take off all of those. So what you look at for this is x squared plus y squared equal to z squared. And essentially, one of the ways you start interpreting these is, what if you hold one of the variables to 0? So suppose, in this case, let's suppose let's just do x first, do it in the order that we see them. So if x is 0, you get basically this. So if we say x equal to 0, then we have y squared equal to z squared. Or you can rewrite that as y equal to plus or minus z. So those are lines in the yz plane. So if we just drew the yz plane over here like this, then you're getting these lines, right? You're getting the plus case and the minus case. Like that. And so with the minus z squared, basically what ends up so that's what you get, but you have these when it fills all in. So you end up with these circles here like that, and you can see that that's a cone. One thing to also see too is x squared plus y squared. What if z is 0? You get 0. You get the only thing that satisfies that, because x squared plus and y squared are both positive always, is you get just 1 point. You get the origin right there. X, y is 0. So it comes to a point at that value. So the way you draw that one is pretty easy. You just draw it's a circle, but it's an ellipse on top. Oops, I hate when it does that. Let's try that again. Did it again. Okay. So circle and then oops, like that. And then it just comes to a point in the middle. So the middle of this is here, like this. And so it comes like that. And this would just keep on going. So you can just do this. Really the way I drew it the first time is how you want to do it. So there's your cone. And again, you can go in the back and put dots and stuff. Like that. All right, one thing I want to show you on this one, if you solve for z, and this comes up a little more later, but I'm just going to show you. If you have x squared plus y squared equal to z squared, and you solve for z, you're going to get plus or minus the square root of something, and that's x squared plus y squared. So that, when you put in that root, sometimes it's hard to see what that is. Well, basically, the plus case of the root gives you the top half of the cone, and the minus gives you the bottom half. And it's a function of those two variables. So it is a function. So we end up talking about that too, functions of several variables in the next couple chapters. Okay, so that covers all of them. And then the summary in the book is what you basically need to know. I have that whole page here copied. Okay, so I'll just leave that there because you can see it. I won't go back and put it in there for my other notes. It doesn't really matter. But we can talk about it here. So this is what you need to know. Now, the only thing different is we might open a different size. We might open along the y-axis or something like that and do this. come out along the x-axis, and it'll be like that. And I'll show you a couple different cases of what those look like. All right, so what I usually do next is we go into the book and identify some of the problems, and I also show you stuff on the graphing program. So let's take a look at that. I got one all ready to go here. Take a look at this function at the top. Again, I can't point in this program. So the top one is x squared plus y squared plus z squared equals 4. So we know that should be a sphere. So here's my sphere, right? Looks pretty good. Note that if you, we can change the, see how it's not exactly perfect? It's because it's putting in values. It only does so many values. If you zoom in too far, it shows weird stuff. Like there's no holes in that thing. It's just, you're just not graphed right. So then if we go in and change that, then we can, let me go to my list here. We can go in and make that something different. So if I put there, if I divide now and make that, I don't know, divide by 4, suppose, then that's going to now be that's going to be a ellipsoid. Sorry, that's not a sphere anymore. That's an ellipsoid. So let's look at that. And you can see I'll zoom in so it gets everything. So there's my ellipsoid. Okay, so has the same general shape to it, but now it looks like that. And you can see the XY. Sometimes it's hard to control this thing. Over here, so that's the basic orientation we like to see. You can draw it like that. You can see the ellipsoid. Okay, let's do some other ones. Let's go back here. Let me get rid of that. Okay, so let's go back to my list. Let's see. Oh, this one. Okay, so this one. Oh gosh, I just realized I forgot an important one that we didn't even do here. The paraboloid. So this is a paraboloid shifted up 1 unit. I'll go back and finish that. So there's your paraboloid that opens up. Right? And it doesn't matter how far out you zoom, it's always going to be there, right? So, okay, so that opens up one unit. You can move it down, right? So this has the +1. If it's not there, then it's going to be at the origin. Here's your hyperbolic paraboloid. Right, and it goes up on both sides. Let me put it like that. You can kind of see that. There's your paraboloid down, paraboloid up. See how that basic picture is. So hyperbolic paraboloid. Try to get them all in here. Let's see. What's this one going to be at the look at the very top, whatever color that is. 4 minus x squared minus y squared. That should be a paraboloid that opens down, right? Because 4 minus x squared is just a parabola that opens down. 4 minus y squared, again, parabola that opens down. Right, so there you go. That's a parabola that opens down. Paraboloid that opens down. I didn't actually show you in the writing. Whoops. Okay, so that opens down like that. Okay. Let's keep going here. I think these are my other ones. Notice the capital F on this one here. I'll try to put it at the top. Well, not quite the top. Notice the capital in the purple one, darker purple. F of x, y, z, x squared, y squared minus z squared equals 1. That's which case is that? That's got to be one hyperboloid of 1 sheet or 2 sheets. So 1 negative means 1 sheet, and so you can see it's 1 sheet. Like that. Okay, and zooming in and out sometimes on this. So a lot of the programs, at least when I bought this one, most of them were free, but I had to buy this one to get it to do it implicitly. So this is called an implicit function of x, y, z. Right? It's basically like a function of it's called implicit. Okay, I'll get into that more later, but there's your 1 sheet, and then the next one is 2 sheets. Okay, there's your hyperboloid of 2 sheets, right? Both x and y are negative. I think I like the wireframe the best. I don't know. What do you like the best? Oh, good. Wonderful. All right, so let's see what else we got. This should be a cone set equal to 0. Yeah, see? I have x squared plus y squared minus z squared equal to 0. But you can't, the way you graph this and write it up, you can't bring over the z on one side. You have to write it equal to a constant. So that's the implicit form. This should be a cone, the next one. And there you go, it's a cone. And you can see it's, little pixelated, if you want to call it that. Let's do it in the sheet. It doesn't look too bad, but you can see the little bumps in it. It's just plotting a bunch. But it comes to a point, though. Right at the center, it comes to a point. Nothing's square. You see that kind of square thing? Nothing's square about it at all. That's just the program. And if you can make them look really good the more iterations you do, more powerful programs. But this is just an older one with an iPad. I mean, they're pretty good. Pretty good an idea of what they are. Let's see. I think that covered everything. Yeah, we hit everything there. Okay. So that's it. Look at a few examples a little bit later, probably in the problem sessions to cover those. And that's it for chapter 12. This is a little separate section to just introduce you all this stuff. But what we're going to do, the future of this might look something like this one. We might take, I wanted to show you this cylinder. There we go. There's a cylinder. That cylinder opens right along the x-axis. So we might take a cylinder like that and say, I don't know. Not that one. Let's do that one. Might take here's an example. So if I move this one down, let's change this to I'll move it down to the origin. So how do you find the volume between the paraboloid and the cylinder? So you're going to integrate. This is not until chapter 15. But what's the volume? Look at that intersection. Like, how does that work? Like that little piece in there. It's everything's curved. Like, there's symmetry we're going to be able to use, but that curve and how you find that is not a trivial thing. That's the sort of stuff we'll be looking at in chapter 15. Okay, I think that'll do it.